This is the Discovery Files podcast from the U.S. National Science Foundation. Cement is the most widely consumed material globally. It is ubiquitous. You're surrounded by it. And if you're anything like this narrator, you rarely consider it. The EPA has estimated the total greenhouse gas emissions for 2020 as 5,981 million metric tons. A single metric ton would fill up a 26-foot, 8-inch square, or a sphere 33 feet across. According to a report by international think tank Chatham House, the cement industry accounts for 8% of human-caused greenhouse gas emissions. These emissions trap heat in the atmosphere, compounding the effects of climate change. But these environmental impacts aren't the only costs. The USDA estimates that 1 mile of a single-lane road has cost between $11,000 and $15,000 per year to keep in good repair. That cost increases exponentially when you're looking at freeway construction. The United Nations predict that by 2050, 2/3 of the world population will be concentrated in cities. With such a dynamic trend towards urbanization, the production of cement is expected to skyrocket. If we continue to produce cement in the same manner as we have historically, that will mean a great increase in materials consumption and massive amounts of CO2 emissions. Supported in part by NSF, researchers are looking for solutions, making better materials and making better use of the materials we have. At Northwestern University, Angie Akono has found that by introducing nanoparticles, a more durable, more resilient cement can be formed. Can you explain the difference between cement and concrete?
Because cement is a part of concrete. So cement results, in this case, from firing up limestone and other raw ingredients at a very high temperature, around 1500 degrees Celsius. And this is how we're really going to have this highly reactive powder that is cement. And later you're going to mix cement and then stone and sand. This is going to lead to what we call concrete. This is kind of the traditional cement that we're using before. When you have cement, you have different type of ingredient in the clinker in this case. And they call calcium silicate hydrate. You can have, for instance, a light, or you can have a light in the cement that we have. What is really interesting is that Portland cement now is really a major part of our civilization. Concrete is the most consumed material in the world. The annual consumption is about 16 billion tons per year. The issue is kind of, when you look at cement, is really the synthesis. So I told you need to have limestone, and you're going to heat it at a very high temperature, 1500 degrees Celsius. And this is going to release just the reaction, and also the heat that you need to produce is going to release a lot of CO2 emission. So right now, the production of 1 ton of cement is going to release 1 ton of CO2. So because of it, there is a strong need to be able to develop new formulation of cement that will be greener, but also more sustainable in this case, just to make sure that we can mitigate climate change moving forward.
How does your nanoparticle cement work?
So what we've discovered is that when you put nanoparticles into the cement, then you're going to be able to have a tougher material. So some example are carbon nanofibers. And essentially what you have is really sheets of carbon. And the thickness of it can be just like 15 nanometers. And then the dimension tend to be on the order of 4 micron by 4 micron. What is interesting is they have what they call a high specific surface area. So this is going to promote, in this case, the hydration reaction. I talked about the raw powder of cement, manufacturing of cement, the clinker, and then we shifted to concrete. But to be able to have that reaction, what you're going to have is you take the clinker powder, you add water, and then you have the aggregate. Now, when you have the clinker powder and the water, then the raw grain are going to react to form calcium silicate hydrate. So you have that hydration reaction. And then you have different building blocks, low density versus high density calcium silicate hydrate. It's almost like the DNA of cement, if you want. And what we've seen is that with carbon-based nanomaterial, we are really able to tailor the DNA of cement to be able to yield the cement that will be tougher, but also more durable. So not just tougher in terms of more resistance to crack, but in this case, we are also changing the pore structure. So that's another aspect of cement, is how does it resist to water transport? within the material. Because another issue with cement is if it absorbs too much water, then this is going to weaken the cement. And what we've been able to do is by using carbon nanomaterial to increase that resistance to water penetration.
Can you explain the role of fracture mechanics in this research?
Fracture mechanics, the way I think about it, is a language. A little bit like English or French, but a formal language to describe how materials are going to resist fracture. So cracks are really pervasive. So you can think of just like if you drop a mug, this is going to shatter. Or you can think, for instance, if you have an iPhone, on the screen of it, you're going to have a crack. Or if you walk on the street, on the pavement, you're going to see cracks. Or if you have an old home, then sometimes on the wall, you're going to start seeing little cracks. So fractures are really pervasive. Even in the human body, you have like micro fracture that are being healed every day. So it's really pervasive. There are some applications where you want to prevent fracture, and usually it is most engineering application, or even you can think of biomedical applications. And then you have some applications where you actually want to induce fracture, control fracture. So you can think, for instance, in energy, when you think of unconventional resources, or when you think of fracking in this case. Another issue when we think about fracture and the relevance of it is really the huge cost. If you think about it, fracture costs close to 4% of the GDP. And you don't think about it, but that makes sense. Like if your iPhone breaks, typically then if you have a fracture, then you're going to have a loss of functionality. So you need to get a new one. Or if the mug breaks, then you will need to replace the mugs. So this is going to lead to high maintenance costs. Like in civil engineering, for instance, if you have a crack, then you're going to weaken the structure. So you need to have maintenance to prevent catastrophic failure, to prevent loss of human life in this case. So this is why fracture mechanics is really there to understand how do materials resist fracture. So now we focus on cement in this case. How does cement resist fracture? And how can we then design a stronger and a tougher cement? So here the adjective is tougher. So that means it's going to be more resistant to cracking.
So how would a smart cement change the world?
Well, it leads to more resilient structures and infrastructures. Structures who are going to be able to endure events or even loading without breaking or without fracturing. One immediate consequence is reduced maintenance cost. Because you need to have less maintenance if the crack takes longer to propagate in this case. So that you really have this kind of saving. Another consequence is when you think about roads or even structures, if you have less constructions, you're going to also have less disruption, because it's going to be less disruption and to functionality. So for instance, typically during the winter, you have a lot of traffic just because of just like construction, maintenance of road. But if you have a road that is more resilient to fracture, then you have less construction. That is one aspect. Another aspect is just going to be also more connection in this case. And that's very important when you think about cities. Cities are becoming kind of this meeting point where more people are coming. Well, a lot of our buildings are exhausted. They are at the end of their lifetime. But if you have a tougher cement, then you can prolong the life structures. You can have more people together. You can create more values in this case. So that would be kind of my three points. You save in budget, you also save on time, and then you just build more connections.
What other advances are you working on?
We are focusing now on just resistance to heat. And one of the reasons is just the heat wave sweeping the country and even the world in this case, because you have more extreme weather or even kind of lots of wildfires that are going to be stronger in magnitude, frequency, and intensity. So we're really trying to understand now what is the potential of nanomaterial to yield a cement that is going to be more resilient in this case to those extreme weather condition. Another area is how can we think of a different formulation of cement that does not use Portland cement. Cement is really good. The challenge is because of the large volume that we're using, and because to produce 1 ton of cement, you still need 1 ton of CO2 in this case. So we've really been thinking about just like how can we have alternative to cement that are going to be greener, that will be using local material and still have the same standard of performance. And finally, a third direction that we've been focusing on is just recycling concrete. A lot of our structures are at the end of their lifetimes. What happened to that construction and demolition waste? Well, that construction and demolition waste represent 30% of municipal solid waste, and 2/3 of that 30% is going to be concrete. So we've been thinking about what if instead of going to landfills, we can recycle it, just like we are recycling plastic now, right? And we've been kind of working with different ways, just understanding first recycle aggregate concrete, but also thinking about how can we tune it and make it better so that in 10 to 15 years, the standard will be, well, if I need to demolish this house, I can just reuse the same concrete to build another house.
At the University of Wisconsin-Madison, Bu Wang and Robert Anix are working to decarbonize cement manufacturing. They are developing a low-temperature calcium hydroxide using waste materials such as coal ash. This new cement process could drastically reduce carbon emissions and clean up landfills at the same time. How did you become interested in carbon capture?
So climate change has always been an important issue to me personally, but I wasn't really aware of carbon capture until I really started to look at the numbers, how much emission we're generating.
I was working in the defense industry and at some point got more interested in environmental issues. Climate became a big issue, is obviously a big issue. After working in biofuels for a decade or so, I realized that probably wasn't going to solve the problem, and we're getting farther and farther behind instead of catching up. And we've moved into trying to find ways to pull carbon directly out of the atmosphere.
Dr. Wang, how would the low-tech technology revolutionize cement manufacturing?
So the low-tech technology we'll propose will hopefully make concrete manufacturing a complete circular economy. It will reuse material as a whole from start to end, but also it will reuse them with a very low energy input. Just in the US, we have billion tons of coal ash just in the landfill that's just left unused, even though people have been working to use as much waste as possible in construction. So nowadays, we are trying to use as much waste material as possible. So a lot of concrete structures, when they got torn down, they are crushed into aggregates, into rocks, and used as fill materials. But they were never truly recycled in terms of chemistry. There are technology out there who have tried to do that, but nonetheless, they still need to use high temperature synthesis, still generate quite a bit of carbon emissions during that process. So the low-tech technology we are working on really is to try to find a low energy cost way to recycle.
Dr. Anix, can you tell me about the X Prize team you put together looking to capture carbon directly?
So Bu was part of an X Prize team when he was a postdoc at UCLA. And when this X Prize competition to do direct air capture, pull CO2 out of the atmosphere arose, he was the main cheerleader saying, hey, we've got the right people here at the University of Wisconsin to work on this, and we ought to pull some students together. So we sent out a call, and the Energy Analysis and Policy program provided students that are interested in the social aspects and some of the economic and policy aspects, and a lot of engineering students who have been in Bu's classes or my classes, brought technical expertise, and we formed a team, and the team won the largest prize that's possible as part of the X Prize competition.
You also have a special partnership for finding talented graduate students. Can you tell us a bit about this program?
There's lots of talent out there that we're not taking advantage of. And so we have a partner in Fort Lewis College that is a wonderful undergraduate institution that helps essentially groom students for the kind of research that we're doing. So being able to involve them when they're undergraduates, they are working on related and important technologies. They can come and spend a summer with us, and it makes them ideal graduate students. If they're going to an institution that doesn't have a lot of research, being able to team with a program like ours through the NSF funding makes it possible to access those people.
How is NSF funding impacting your work?
NSF funding is really amazing because it lets us work on the fundamentals, and they also have special programs that they'll pull together to address important topics that are transdisciplinary or multidisciplinary. And I've had funding from several of those. It's certainly been a prime part of making my career successful. And given that I think climate change is the biggest challenge facing our generation today or the world today, and with NSF funding, we're able to do something that will really, affect that.
At the University of Delaware, a team working under Professor Norman Wagner is looking at geopolymers and looking ahead to construction on the Moon and Mars to see how we can prepare for future space missions. We spoke with Jennifer Mills, who worked on her PhD on this team. Dr. Mills, why are geopolymers a potential solution for lunar construction?
On Earth, people that are doing geopolymer research pretty much make them out of anything that has a high concentration of aluminum or silicon, so aluminosilicate materials. And these are things like clay, metakaolin, or fly ash is a popular one, which is a byproduct of coal combustion. And so these fly ash geopolymers are commercially available on Earth now. So the reason that we think geopolymers are a solution for lunar construction is the lunar regolith has a high chemical similarity to Class F fly ash, which is already being used on Earth. So we can take a lot of those learnings from the field for applications down here and use it to inform making these lunar regolith geopolymers.
What is regolith?
So that's the top layer of soil that's present on the surface of the Moon or Mars. So just kind of that initial layer of freer soil that's the outermost layer.
And why do we need a simulated regolith?
Obviously, we want to study the regolith that's present on the surface of the Moon or Mars, but we don't have access to large quantities of the material that we would need to conduct our research. So NASA and other space agencies, as well as private companies and academic research groups, will design their own soils that are meant to simulate the regolith. And this is meant to mimic the physical and chemical properties of the regolith that's been either brought back from the Apollo missions or recorded by the rovers, or just based on other data that's available. Because we have all of these different groups that are sometimes designing their own simulants, there can be a lot of variability in the simulants that are being designed. So sometimes this can be in the composition, there's ranges of the chemistry that's available, or also in the material properties. And also some of these groups, they're specifically designing them for certain purposes. So maybe they're more worried about the chemistry and they want that to be as close as possible, but some of the physical properties will be a little bit different, or they're more worried about the physical properties and they don't care as much about the chemistry. So in this study, that's one of the things that we wanted to look at. How much does that variability play in? And also some of these simulants that are meant to mimic like different areas of the Moon. So we looked at both a mare simulant and a highland simulant. So there's some differences in the chemistry and properties of those. If people are just making binders out of these simulants, can we compare them to each other, or do we need to be really looking at exactly the same type of simulant from work to work to be able to understand the differences? And so in our study, we made a bunch of different binders under exactly the same conditions using these different simulants so that we could see what the differences were.
What sort of testing did you consider for lunar construction?
We wanted to see how strong the cements were. And then we wanted to look at them under different environmental conditions that might be relevant for this type of application. So to test the strength, we basically just crushed them between two plates. And so we looked at some that were just cured under ambient conditions, using that as kind of a control. And these are ambient terrestrial conditions, but that's obviously the easiest thing for other scientists to replicate, and we needed a baseline somewhere. And then some of them were placed in a vacuum and they cured in a vacuum for the whole 7 days. So that can show us if the reaction is able to take place in a vacuum or under these low pressures. And the strength was lower under the vacuum, but we were still able to record something. And so that tells us that depending on what the sort of target value is, that might be good enough. So you might be able to get away with having the reaction take place under these conditions, or if you're going to need a higher strength for whatever is being built, then maybe it needs to be done in like a pressurized environment or some other way. The other things that we looked at were high and low temperature exposures. So some of them were exposed to low temperature, which was -80. We tried to cure them for the whole 7 days under these conditions, but we basically found that the kinetics were so low, the reaction was so hindered that we weren't able to form basically anything in the time scale that we were looking at. So instead, we allowed them to cure for a couple of days under ambient conditions and then exposed them to the lower conditions. And again, we saw that this lowered the strength as we expected. So the temperature is something to consider. And then we also looked at high temperature exposure, which was just putting them in a furnace for an hour at 600 Celsius. We talked to some people at Kennedy Space Center, and they let us know that one of the things that will be most important to build are these takeoff and landing pads for the rockets to protect them from debris. And so if these materials are being used for that application, they might be subject to very high temperature. And so we weren't able to mimic exactly, a rocket taking off. What we wanted to look at was traditional cement usually fails at about 400 Celsius. So we wanted to go above that with our geopolymer binders because from the literature, we saw that they've been shown to have superior high temperature performance. So we chose 600 Celsius just to see if we're even on the right track. And we found that this didn't adversely affect the strength, but it did change some of the material properties. And so going forward, that would be something that we could study further.
What will be some of the challenges applying this research in space?
In situ resource utilization is definitely going to be important for space exploration because we can't feasibly ship cement to space for construction just because of the cargo space and also the cost that would be associated. On top of that, in OPC, you're reacting it with just water. And so we are thinking that water might be necessary for making the geopolymers because you need some sort of medium to help dissolve the ions, but the water doesn't actually chemically participate in the reaction. So there's a little bit more flexibility there. The application is kind of a whole other thing. And I think that there's going to need to be new engineering solutions for that as well. And it's probably not going to look exactly like how we build things on Earth. One thing that's a growing field in just regular cement, but also geopolymers, is additive manufacturing and just sort of automating a lot of these processes. And I would imagine that in space, they're going to need to be using some robots to help with things as well. So I think that that will probably be part of the solution, or also making things one place and then kind of implementing them and in another place rather than just pouring it directly wherever it needs to go, because that might help mitigate some of those issues. But yeah, definitely a lot of interesting challenges.
Finally, if you had the opportunity to travel to space to implement your research, would you go?
Yeah, that's a good question. I feel like you can't say no. I would definitely want to be involved in some way. It's hard to imagine actually going to space. I'm not a big traveler, so I think that the logistics would be a little stressful for me. But yeah, I think I would have to do it. That's a once in a lifetime opportunity. And to have your own research sort of being implemented, that would be awesome.
Special thanks to Jennifer Mills, Bu Wang, Robert Annex, Angie Akono, Robert Corland, Terrence Affer Anderson, Adam Eggers, and Dina Headley. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts. And if you like our program, consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.